Hi, thanks for tuning in. My name is Jack Kodros. This talk is on the aging of biomass burning aerosol plumes in the dark as a possible overlooked source of oxidized organic aerosol. So I'm specifically thinking of these elevated concentrations of oxidized organic aerosol that have been observed in urban environments in the winter or at night or at other periods of otherwise low photochemical activity. So of course, biomass burning has direct implications for air quality and climate. But we want to think about what happens to this plume after a week or a month. Can we even differentiate it from other emissions after it's been processed in the atmosphere? This is important because the oxidized organic aerosol that's formed from these aging processes is the background aerosol concentration that continues to impact climate and health throughout this period. When we normally think about oxidation of organic aerosol from biomass burning, we usually think of it as a photochemistry dominated process where the hydroxyl radical reacts with gas phase compounds to form oxidized organic aerosol in the presence of sunlight. And this has led to improved representations of oxidized organic aerosol in models. So this study was by Fadoukas et al. 2016, and it's showing comparisons of simulated and observed OA in Paris, France in the winter and the summer. So the top two plots are showing primary organic aerosol comparisons in the summer and the winter, and the model, as you can see, does a fair job of reproducing these concentrations. And actually, the model also does a pretty fair job of reproducing oxidized organic aerosol concentrations in the summer. But where the model really fails is in the winter. Specifically, there's a large underestimation of secondary OA in the winter time. And the authors speculate that perhaps there's some secondary OA formation process that's taking place during periods of low photochemical activity that's not already included in the model. And in fact, atmospheric models do not include oxidation of biomass burning taking place in the dark. And this is really important because if we want to link biomass burning emissions to oxidized organic aerosol, and we are missing this oxidation mechanism that may take place at night, we are underestimating this link to oxidized organic aerosol and therefore underestimating any associated impacts on health and climate. So to look into this, we performed a measurement campaign in Patra, Greece, which is a typical urban environment in the winter where it's impacted by residential biomass burning for heating. So in the daytime, we can see some similar features in this diurnal profile of NOx and O3, where we have a peak due to morning rush hour combustion in NOx and a late afternoon ozone peak due to photolysis forming ozone. We also find a nighttime peak in NOx to residential biomass burning combustions. And this nighttime peak originally consumes all the available ozone in the nocturnal boundary layer. But actually, later at night, we find a secondary ozone peak. And we think this is ozone that was formed during the daytime that resides in the residual layer that's left over above the nocturnal boundary layer. And this ozone can then gradually transport down into the nocturnal boundary layer and react with NOx to potentially form the nitrate radical. And this nitrate radical is a powerful oxidant that has been shown in previous studies, such as in Brown et al. 2013, to react with biogenic volatile organic compounds, and more recently in Decker et al. 2019 with biomass burning aerosol. So when we look at our metrics for OA oxidation, such as the oxygen to carbon ratio, or the fraction of OA at MZ44 to MZ60, we see a consistent picture with the nitrate radical reacting with biomass burning VOCs to form oxidized organic aerosol. So to look into this in more detail, we performed laboratory smog chamber experiments with biomass burning emission plumes, where in our setup, we have a suite of online gas and particle phase instruments, as well as a number of offline analysis for filter sampling, which today I will not go into the offline analysis. I'll focus mostly on the online instrumentation. We can quantify the magnitude of the organic aerosol aging by looking at the oxygen to carbon ratio. In this plot, I'm showing the enhancement in the oxygen to carbon ratio. So the O to C ratio relative to the O to C ratio of the fresh emissions before oxidation happens. In the plots that I'll be showing, oxidation will always begin at an hour of 0. So prior to oxidation, we expect the oxygen to carbon ratio to remain constant at a value of 1. And after oxidation, we expect an increasing enhancement in the O to C ratio, which implies an oxidation process taking place. So when we look at our dark reference experiment, where we inject biomass burning emissions into the chamber and we don't do anything, we don't add oxidants, we don't turn on any lights, we find that indeed the oxygen to carbon ratio remains constant and has an enhancement of 1. We can also look at an experiment where at hour 0, we switch on ultraviolet lights to simulate daytime chemistry. And as we expect, we find that after hour 0, there's a rapid and extensive enhancement in oxygen to carbon ratio, implying an oxidation process taking place. This is the current conceptual model where we have during the day oxidation taking place and at night nothing happening. But in our experiments, we found that when the biomass burning plume was exposed to NO2 and O3, so we injected NO2 and O3 at hour 0, the plume did age and we did see an enhancement in oxygen to carbon ratio following this exposure. We also varied the conditions in the chamber from low relative humidity to high relative humidity and actually found more rapid and extensive oxidation in the dark under high relative humidity conditions. So in the presence of NO2 and O3, biomass burning aerosol plumes can undergo rapid chemical aging without requiring any sunlight. Instead of just looking at the oxygen to carbon ratio, we can look at the enhancement in total organic aerosol mass. And here we find a similar enhancement under conditions with UV lights and in the dark under exposure to NO2 and O3. We will note that there is quite a lot of variability in the secondary organic aerosol formed, as we expect. Something that really differentiates the dark experiments with the UV lights experiments is the enhancement in nitrate aerosol. Here I'm referring to both inorganic and organic nitrate aerosol. In the dark experiments, we found substantial enhancement in nitrate aerosol, where something like 25 to 35% of the produced aerosol was in the form of nitrate. This does not take place in the UV experiments. What we're really interested in is seeing if the biomass burning plumes aged in the dark may contribute to ambient factors of OOA that are observed in urban environments. So here I'm showing the fraction of OA mass at MZ44 compared to MZ43 as measured from the HRAMS, along with our experiments in dark, dry, and high relative humidity conditions. And what we find after a few hours, the total chamber plume ages to be more representative of fresh biomass burning OA factors into OOA factors. When we look at the full aerosol mass spectra, and in these plots I'm showing on the right, we have factorized our chamber experiments into a fresh biomass burning factor and a produced oxidized organic aerosol factor. And when we find both the fresh and aged factors are representative of what is observed in the ambient environment. Here I'm showing comparisons of the fresh and aged factors in the chamber with those observed in Athens and Patra, Greece. So we next incorporated a simplified mechanism of dark aging into a chemical transform model, PM-CAMX, to see the relevance for the atmospheric process. And when we find when dark aging is included in the model, we find an increased conversion rate from fresh to aged organic aerosol. So in these plots, I'm showing the percent change in primary organic aerosol from biomass burning and oxidized organic aerosol from biomass burning, the latter of which increases throughout the US. Finally, we can also quantify the ratio of oxidized organic aerosol that underwent some NO3 radical reaction at night versus the total biomass burning OA. So this is the sum of both fresh and aged organic aerosol. And what we find in active fire regions, something like 5 to 20% of the total biomass burning organic aerosol has undergone some dark oxidation process. In smaller fires, this ratio may be something more like 40%. Downwind of fires, though, we find that something like 60 to 75% of the total biomass burning organic aerosol has undergone at least one dark aging process. So what we found is that after exposure to NO2 and O3, biomass burning organic aerosol can rapidly form oxidized organic aerosol in the lab without requiring any sunlight. The produced oxidized organic aerosol is similar to the factors that are observed in ambient environments, suggesting that indeed dark aging processes can contribute to elevated OOA levels at low photochemical periods. Finally, when we include a simplified nitrate radical oxidation mechanism into a chemical transport model, we find that up to 60 to 75% of the total biomass burning OA has undergone some dark chemical process, suggesting this may be really something important to include in future models. Thank you, and I'm happy to answer any of your questions.